Hey everyone, some of you asked me to record an inference overview video, just kind of going over one of each type of inference. So I thought I would do it in the form of this document, which is called AP Review by Topic. It's in your AP Review file where it says AP Review by Topic. And if you click into it, you're going to see it look like this. I'm going to scroll over until I get to the inference part of this, which is going to be called Topic 4. Topic 4, statistical inference. And I'm going to start doing some questions, one of each type. I'm not going to necessarily do all of them. I'm not going to really do them full out, but I'm just going to kind of discuss how to approach them. So if you look down at number 23, 23 said, what is the general form for all confidence intervals? I know we've been going over this in class. So we need to make sure that we remind ourselves that this is a formula on our formula sheet. And the formula for any confidence interval is statistic plus or minus critical value times standard error of the statistic. So we're going to use that when we do our confidence intervals. So the first one says, suppose there's a random sample of 50 bottles. So I would circle that, and right away I'm going to write N equals 50 of cough medicine, and alcohol content of each bottle is determined. Let mu denote the average alcohol content. So notice we're saying mu equals the average. So right away, this is a mean question. And it's a mean question because it says average. For the population bottle of all bottles. Suppose that the sample mean is 8.2. That's X bar. And the standard deviation is 1.5. So I'm assuming this is the sample standard deviation, 1.5. Now, these numbers are called statistics, and they're called statistics because they come from the sample. So it says finding 95% confidence interval for the mean alcohol content of the cough medicine and find the margin of error. Okay, so notice we have the word interval. Interval starts with the letter I, and interval is in the word panic. Panic has an I in it for interval. So if we were fully doing out this question, we would be doing the panic steps, okay? Let's talk about some. The P is the population of interest and the parameter of interest. The parameter is what we just discussed, which is the U. And it's in words, the true mean or true average alcohol content for the cough medicine. And you can really just use the words that are right out of the question, mean alcohol content for the cough medicine. So that's the parameter of interest, and we're using the letter mu. Okay, so we would do the assumptions. If we did do the assumptions for means are, is it an SRS, meaning is it a simple random sample, which it says it is a random sample of 50 bottles. So we're going to assume it's a simple random sample. Is 10 times N less than the population of interest? So it's 10 times 50, which is 500, less than the population of all cough medicines of this cough medicine of this particular brand. That is the population of interest, all bottles of cough medicine of this particular brand. Hopefully it is. And lastly, central limit theorem. If N is greater than 30, which it is, then by the central limit theorem, the sampling distribution will be approximately normal. And I'm just kind of abbreviating here, okay? So as you guys can see, our assumptions are met. So then we have the name of the interval. The name of the interval, because it's one sample of 50, is a one sample. And you have to decide, is it means or proportions? We said it's means, so it's going to be T, because remember for means we use T if we don't have sigma, and we're using S in place of sigma, which we are. We don't know sigma, it's unknown. We're going to use a T interval. This is called a one sample T interval for means, okay? Now the formula for the interval itself. This is the step where you guys need to write the formula in symbols and then in numbers. So we said the formula is statistic, which is X bar, plus or minus critical value, T star, times the standard error of the statistic, the standard error of the sample mean. So now we're going to plug in what we know. The statistic is 8.2. Plus or minus T star, we're going to have to look up. The standard error is going to be 1.5, which is S, over radical N, which is radical 50. So remember, to get T star, we will go to table B, which is for T distribution. and we would look up the degrees of freedom, which is n minus 1. So if we did 50 minus 1, we would get 49, and we would look to see if it is on the table or not. If it is not on the table, what we could do is just leave the T star empty, and you could write DF49, and then you would just go to your calculator for the answer, and then you would make your sentence. So you say, I am blank % confident the true blank is between blank and blank. So I am 95% confident that the true mean alcohol content of the bottles of the cough medicine is between blank and blank. And then I would go to my calculator, I would go to the one sample T interval, I would plug in all the information in data or stats, you would choose stats, and then you would just run the interval and you would write your answer. So remember, if they ask me about the confidence level instead of the interval, you would say, if I repeat this process many, many times, 95% of created intervals will capture the true mean alcohol content for the cough medicine. Now, if you look down to part D, this is like a little addendum to this question. It says the manufacturer claims that the mean alcohol content is 8. So notice we have the word claim. So as soon as you see the word claim, it seems like we're doing hypotheses. So the HO is the claim that mu, which is the mean, the true mean, is 8. So that's one mean because this is a one sample question. And then the alternative hypothesis would be whatever we're trying to prove. So we will go back to the question and see if we were trying to prove something specific. So it doesn't necessarily say that they're speculating on anything. So, I mean, we could just put not equal to here, and then we would be good to go. And then basically, we're not going to do the P step again. We're not going to do the A step again. The N, the name, is just going to change now because it's going to become a test. So this is going to still be one sample T, but now it's going to be a test. So now when we do our test statistic, which is for phantoms, the T step, test statistic, the test statistic is going to be a T-score. So your formula, remember, for any test statistic is going to be statistic minus parameter over standard error of the statistic. So in this case, we would do statistic, which is x bar, minus parameter, which is mu sub x bar, but mu sub x bar equals mu, over standard error or standard deviation of the statistic. Standard deviation of the mean is usually sigma over radical n, but we're going to use s over radical n because we don't know sigma. So that's why it's called standard error. So s over radical n. So I would substitute in what I know, the x bar from above, minus the mean 8 over the standard deviation from above over radical 50, okay? So now plug in what you know, 8.2 minus 8, the x bar was 8.2, over s, which is 1.5, over square root of n, which is square root of 50. Now you would just go to your calculator. After you write this in, you would do stat, and you go over to test, and you choose the one sample t-test. I think it's number 2. I think it's just called t-test. And then you would just plug in the information again, and you would run the test, and you will get your p-value, and then you would either conclude to reject the null or not. But you could also go to your interval from above, and I didn't actually do the interval here, but you would look at the endpoints of the interval, and you would see if 8 lies in the interval or not. If 8 lies in the interval, it's plausible, and you fail to reject the null. But if 8 does not lie in the interval, it lies on the tail, then you would reject the null because the p-value would be low. Okay, this is the first type of procedure, the one sample T interval and one sample T. Now we're going to go over to number 25. Let's read the question. It seems like the question says the word proportion. As soon as you see the word proportion, I would write PZ. Proportions, we use Z. This news service reported that the proportion of all households that use coupons is 0.77. So hopefully you see the word all and you think, oh, that's a parameter. Specifically, the parameter is P, and that's 0.77. And that's what's reported by this service, okay? Now, if you reread the question, it sounds like we're doing a sample of size 800. And it sounds like this estimate was based on a sample of 800. So we're not actually going to call this P. We're going to call this P hat because it seems like that number was from the sample data. And what we're going to do is create an interval around the sample P hat in order to calculate the true proportion P and estimate the true proportion P. So as you can see, this is a 99% level. So I would write that down. I would also note that because this is proportions and we're using Z star, that we could just look up 99%. So you would look up the Z star for that one. I think it's 2.576, but I don't have it in front of me. And then what you would do is you would start to do your procedure. So remember, if it's an interval, it starts with the letter I, so it's going to be panic again. The population of interest or parameter of interest, we'll start with population of interest. It seems like it's all households. And the parameter of interest is going to be P, the true population proportion of households that use coupons. So make sure you're writing the word true proportion instead of true mean here. True proportion of all households who use coupons. Okay, so notice the last question was a mean question. This is a proportion question. So make sure you define your parameter correctly. If it's a proportion question, you say proportion. If it's a mean question, you say mean or average. Now we would do our assumptions. For proportions, our assumptions are still SRS, still 10N is less than the population of interest. But instead of doing central limit theorem for means, we have to do NP hat greater than or equal to 10 and NQ hat greater than or equal to 10. If those are met, the sampling distribution of P hat will be approximately normal, and we could proceed with the name of the procedure. The name is called a one proportion Z interval. So the last one was means, and it was a T interval. This is proportion, so it is a Z interval. It's still only one sample, so it's one proportion, okay? So now we're going to do the interval step. So remember the interval step is statistic, which in this case is P hat, which is this one, plus or minus Z star times sigma P hat, which is the standard deviation or standard error of that statistic. So P hat was reported to be 0.77 from the statistic sample. The Z star you would plug in, and the sigma P hat is the square root of P times 1 minus P over N. Now, if you don't have P, you have to use P hat in its place, and that's why it becomes the standard error instead of the standard deviation. So basically, I would just plug in here the P hat that was given to me, which is 0.77, 1 minus 0.77, and the sample size 800. And I think the Z star, like I said, I think it's 2.576. I can look it up, but then you get your interval and then you do the same thing. But you say, I am 99% confident that the true proportion of all households who use coupons is between blah and blah. So you're just using the word proportion instead of mean. I just looked it up and it is 2.576 for 99%. So then we go to part B. It says the manager of the the manager of the retail store is reporting to his superiors claims that the true proportion that use coupons is 80%. So they're claiming that the true proportion is 80%. This is the claim. So again, the test is the one where you have the word T, test. So that's a test. So then you have to do phantoms here. So again, phantoms, we're not going to do the full P step. We did the population above the parameter of interest above. We're going to go to the hypotheses, okay? So the null would be one proportion, and it would be the parameter. So the parameter for P proportions is P without a hat. So we'd say P equals 0.80. That's the claim. And then the HA would be something different. So basically, it would depend on whatever it says. So maybe he's claiming that it's greater than 80%, less than 80%. If you're not sure, you just could put not equal to 80%. Now again, if the null, the 80, if it's in this interval, you cannot reject it. You fail to reject the null. But if the null is not in the interval, it would be in the tails. And remember, if it's in the tail, the P is low because the tail in this case would be less than 1%. So you would reject the null and you would say that you have enough evidence for the alternative hypothesis. Let's get into the test statistic for this question, okay? The test statistic would be called a Z-score instead of a T-score because it's proportions. And the formula is statistic P hat minus parameter mu P hat, which equals P, over standard deviation or standard error of the statistic. So if you have P, you plug in P here. And if you don't have P, you plug in P hat. Above in part A, I plugged in P hat in this formula. But here, we're claiming that the true portion now is 80 in the null. So you're going to use your claim from the null. That's why I'm putting a sub-0 there. So your P hat was 0.77. Your P is 0.80. And so you're going to do 0.77 minus 0.80 over square root of 0.80, 1 minus 0.80, which is 0.20, over the sample size 800. Now you're going to get a z-score. You're going to get a p-value. You're going to put it in the calculator. You're going to go to stat, go over to test. You're going to choose the one that's called the one proportion z-test. So the name before was a one proportion z interval above. Now it's just a one proportion z-test because we're doing a test now. So you're going to get your z-score. You're going to get your p-value. Then remember, you're going to decide if you're going to reject the null or not, depending on if it's less than 0.05. So now we did one sample mean t interval, one sample mean t test, one proportion z interval, one proportion z test. Now, if you go ahead to number 28, we're talking about males and females. Are girls less inclined, so I'm going to circle that, less inclined to enroll in science than boys? I hope not. One recent study showed randomly selected 4th, 5th, and 6th graders how many science courses they intend to take in high school. Following data is shown below. So we have males, we have females. So right away, I'm hoping you're saying now this is two groups. We're hoping this is two independent groups, which you want to assume when you're doing your assumptions. They don't influence each other. And it says that they were randomly selected, so that's good because that's another one of your assumptions you're going to check. We're going to let group 1 be males, let group 2 be females, or even better, let group M be males and let group F be females, okay? Now, this is sample size 1 and 2, or M and F. This is mean 1, I'm going to call it X bar M, and this is standard deviation for the males, and this is sample mean for the females and standard deviation for the females. All right, so this says construct a 99%, so I'm going to write 0.99 here, confidence interval for the difference between the male and the female mean. So this is difference of the mean. So I would write that down. Difference of the means. So right away, you know this is two groups. This is means. This is still means. You're going to use T because you don't have sigma. You're using S in place of sigma. See, here are the S's. So this is going to be called a two sample T interval for means. So when you get up to your interval step, I'm just going to kind of jump to that one for a second. We just did the name. With the interval step, you're going to do statistic plus or minus critical value times standard error of the statistic, okay? The statistic for the one mean was X bar. So now it's just going to be X bar male minus X bar female, the difference of the means. Plus or minus, since it's means, again, we use T star times the standard error of two means. So you just look that up on the reference table. And for two means, the formula is S1 squared over N1 plus S2 squared over N2. I'm just going to use M here for 1 and F for females for 2. So then you just plug in the information from above. The X bar for males was here, 3.42. It is indeed greater than females in this question for the sample that was those two samples that were taken. Plus or minus. Now T star, you're not going to be able to get the exact value of because you have two samples that are large. So just leave it T star and then let the calculator work its magic later. S1 is 1.49 squared over N1, which is 203, plus S2 of the females over 224. Okay, now again, once you have this all written down, you have your formula and symbols, numbers. Now you're just going to go to your calculator, go to stack, go over to test, go down till you get to the two sample T interval, run it, and then write your interval here. And then when you write your answer, you write, I am 99% confident that, and then just go to the question and read the words that they say. The difference between the male and female means number of courses of science classes planned is between blah and blah. So this is the difference of the means. Just to go back to assumptions really quick, the assumptions that we had to check, which I know I mentioned briefly at the top, are they're both SRSs, but also they're independent. So are they independent of each other, SRSs? Then you're going to do 10 and 1 less than pop 1, 10 and 2 less than pop 2. So you have to do that one twice. And then the last one is CLT, the central limit theorem. If the sample sizes are greater than 30, which they are both greater than 30, it will the sampling distribution of their means will be approximately normal, and because that, the difference of means will also be approximately normal. So approximately normal sampling distribution because the sample sizes N1 and N2 are both greater than 30. Now, if you look ahead to part B, we're going to just build this right into a test. So it was an interval, and now it says the science teacher at the high school for these students plans on attending claims. Sorry, these vocab is horrible. Claims that he claims that there is no difference between the boys and the girls. Test the claim. All right. So as soon as you see the word claim, that means hypotheses, HO and HA. So you're going to make your null hypothesis for two means. Oh, it's two means now, right? Mu1 equals mu2, or mu-m for males equals mu-f. Or if you moved it to one side, mu-m minus mu-f equals 0. In words, this would mean that there is no difference in the mean number of science classes between the two genders. Okay, no difference. That null is always no, no. And the HA is you think that there is a difference. So maybe it's mu M is greater than mu F, because if you go back to the front top, it said that girls seem less inclined than boys. So that would mean boys are more inclined than girls if you'd start with that M for males. So if you move that to one side, it would be mu M minus mu F is greater than 0. Now this became a test. So the name of the procedure now is going to be two samples and its mean. So it's going to be t-test, two sample t-test. So it was called a two sample t-interval up above, right? Now it's just called a two sample t-test, right? Because we're testing a claim. So going back to the test statistic, if you remember on the last page when I started, the test statistic was statistic minus parameter over standard deviation or standard error of the statistic, right? So remember for one mean, it was x bar minus mu x bar, which equals mu over s over radical n. So for two means, it's just going to be kind of double that. So it's going to be x bar 1 minus x bar 2 minus mu 1 minus mu 2 over standard deviation. Instead of this one, we're going to do the one that's a little longer. S1 squared over N1 for males plus S2 squared over N2 for females, all right? So now you would just plug in to the formula just like we did above. So x bar 1 was 3.42 and 2.42. Again, that's going to be the statistic. So the difference between these two was 1.0. Now in the null, you're assuming that the difference between these two equals 0, so you could just put minus 0, or you could just not even write it. And then you would plug in the same thing in here. It's going to actually be the same as above right here, so I'm just going to circle it. I'm just going to put an arrow going down here. All right, same. So then you would go to your calculator, you would find two sample t-test, you would plug in all the information, and then you would get your t-test statistic, your p-value, and then you would decide if you're going to reject the null or not based on the p-value. Remember, when p is low, reject HO. How low? Lower than the alpha level. Now, if you look at this next question, number 29, they're talking about poultry, and they're talking about cooking chicken at different hour marks. And it seems like we want to know if there is a difference in the mean hardness for chicken chilled for 0 hours before cooking and chicken chilled for 2 hours before cooking. So this is where it kind of gets interesting, because you have to decide if this is a two sample mean question or if this is a one sample match pairs T question. So difference in the mean hardness for chicken chilled 0 hours before and chicken chilled 2 hours before, okay? Mean hardness, that's x bar, and this is x. This is the mean of the 0 hours and 2 hours, okay? So I'm thinking this is still a two sample t-test. I'm not going to actually do this one, but I'm just going to say that because this is two separate independent groups, I don't think we're doing this on the same chicken. we're going to do a 2-sample t-test again for this one. Moving on. Number 30. Let's actually move to 31 because I want to move to 2 proportions. So this was talking about softball sliding injuries based on using the breakaway bases, which are the ones that kind of like slide away by Velcro, versus just bases that are anchored into position. So we have some data, and it says, do the use of the breakaway bases reduce the proportion? So look, guys, it says proportion. Write that down. Of games in which a player suffers an injury. So we have proportion of games that they suffer an injury. Perform a test. So I would write the word test. Okay, T. So proportions, proportions we're going to use Z. But test, it has a T in it. So that's a phantom situation because it's a test statistic. So we are going to do, because this is 2 separate groups, N1 I'm going to call S for stationary, and N2 I'm going to call B for breakaway, S and B. This is going to be a 2 proportion Z test, okay? And this is the special one where you're going to pool, okay? So this is the one that you guys had a quiz on where you're going to pool together. So notice this is the number of games. This doesn't say the proportion of games, even though this says proportion. So this is actually the X value of the numerator of the P hat. So what you should do is create a P hat column here and calculate the P hat for both groups. So we're going to do P hat stationary is going to be 90 over 1250, and that's going to be the stationary P hat. And P hat breakaway is going to be 20 over 1250, okay? So you're going to have your 2 sample statistics. And then this is perform a test, so we're going to do phantom. So that means that eventually we are going to need to do the hypotheses, okay? So you would want to do population 1, population 2, parameter 1, parameter 2. Again, if you're using S and B, change it to S and B so that way the person really knows what you're talking about when you're using these subscripts. So I'm going to let population 1 be all games, all softball games using stationary bases. And I'm going to let population 2 or population S be, sorry, I spelled bases wrong, be all games using breakaway bases. And then I'm going to let parameter 1, P sub B, I'm sorry, this is P sub S. P sub S be the true proportion of games using stationary bases. I'm going to just say stationary base games where there were injuries, sliding injuries. I can't spell tonight. And then parameter 2 is going to be P sub B, the true proportion of games using breakaway bases with sliding injuries. All right, so we have population parameter. That's the P step for phantoms, okay? Let's move on to H. The null hypothesis is always a statement of no change, so that's going to be P1 equals P2. We're going to say PS equals PB. Or if you move it to one side, PS minus PB equals 0. There's no difference between the proportions. And then the HA is going to be what we're trying to prove. So if you look back in the question, remember it says, do use of breakaway bases reduce the proportion? So they think that breakaway is going to be less than the stationary. So stationary is going to have greater injuries than breakaway, or you could have written it the reverse. Breakaway is less than stationary. I'm just going to show you this, this method. Okay, so those are the hypotheses. Now, I don't have a lot of room here, so I am going to start a new page for this, but I do want to just mention that we are going to have to pool the 2 proportions together here. So I'm just going to create a pooled P hat because it's important that we do this. I'm going to call this pooled P hat. And remember on the reference table, we call this P hat sub C. So this is a 2 proportion Z test. It is pooled. I went down and I pooled it. I'm going to show you a reminder that this formula is on the reference sheet. You take the 2 numerators and you add them together, 90 plus 20. and that's here and here, x1 plus x2, 90 plus 20. And then the denominators are going to be here and here, 1250 plus 1250. So you're going to get 2500. So we end up getting 110 over 2500, which is 0.044. So that's going to be the full p hat that I use. So I just created a new page here, and I'm just going to plug in the test statistic. Again, I'm going to skip a little bit ahead. The statistic symbols are going to be p hat 1 minus p hat 2. Remember, 1 is stationary and 2 is breakaway. So I'm just going to do s minus p minus b. p1 minus p2, or ps minus pb, is what we're presuming equals 0 in the null. So it's going to become 0 and drop out. And then the standard deviation of the statistic, this is going to be the formula for the special case for the full p hat. So this is the one that you have to go to a different formula than the confidence interval. And that's going to be p hat c, 1 minus p hat c, 1 over n1, or 1 over ns, plus 1 over n2. And then we would just plug in, and we're going to get our z-score, we're going to get our p-value, and we're going to decide if we're going to reject the null or not, okay? So basically that's the setup. You can plug in everything in terms of decimals. You're going to get your z-score, you're going to get your p-value. We only pool for proportions. We only pool for the 2 proportion z-test. So, and a quick reminder that for the assumptions for this one, it's going to be the same as the 1 proportion z-test, but there's going to be 2 of them. So you're going to do, are they 2 independent SRSs? Assume, or just refer to what they say in the question. Is 10 and 1 less than pop 1? Is 10 and 2 less than pop 2? And then instead of central limit there, because it's proportions, you have to do n1 p1 hat greater than or equal to 10, and q1 hat greater than or equal to 10. That's for 1. If that's met, then those are approximately normal at the sampling distribution. Then you have to do n2 p2 hat greater than or equal to 10. N2Q2 hat greater than or equal to 10. If that's met, then the difference of the sampling distribution is approximately normal. And you will proceed with the Z procedure. Let's go down to number 32. It looks like we have one row. One row. It says, does this data provide evidence of color preference? So evidence is going to be a p-value. It seems like they're talking about the color of these birds called bobwhites. And they want to know if we paint the different colors, if the birds are going to prefer the different colors over others. So this is 33 sample size, that's n. And these numbers should total up to 33. And this data down below are the observed counts or actual counts of what actually happened. So we want to know what would have been predicted to happen. Now, if they had no preference for color, then it would just be equally distributed. So there's 4 colors. So we just do 33 divided by 4, and we would get the 4 expected counts, expected or predicted counts, if basically they were all equal. So we would get 8.25, 8.25, 8.25, and 8.25, and those should total up to 33. So this is observed and expected. So this is the chi-square test because they don't say the word mean. They don't say the word proportion. Even if it was proportions, there's more than 2 proportions. So it can't be a 2 proportion z-test. There's 4 proportions here. And basically, if you see one row or one column and it's just one variable at play, but there's multiple proportions, it is a chi-squared test for goodness of fit. Okay, so you can watch my video on how to do that. But remember, the formula is observed minus expected squared over expected. And you would add those all up, and you're going to get your chi-square test statistic. Put it in L1 for the observed, L2 for the expected, and run the chi-square test for goodness of fit. Remember, the degrees of freedom is number of categories minus 1 for this one. So there's 4 color categories minus 1 equals 3. Now we're going to look at number 33. Number 33 is talking about two categorical variables. The two categorical variables are gender, which is the column variable, and workaholism type. So as soon as you see the word independent or association, this is going to be a chi-squared test for association/independence. And this is because there are two categorical variables and there's more than two proportions going on here. There's a bunch of different cells. So just a reminder that these are the observed counts, and you would put these in matrix A. And if you wanted the expected counts, you would put the observed counts in matrix A. Then you would run the chi-squared test for association, which is the one that just says chi-squared test on the calculator without anything. It doesn't say goodness of fit, it just says nothing. And then they would put the expected counts in matrix B. And you would copy those down. You could copy them down right here, or you can copy them in a separate table. And then you run the chi-squared test, you get the p-value and all the test statistic and everything that you need to know from there. I just want to remind you that the null hypothesis for this would be the two variables are independent of each other. So gender and workaholism are independent. Workaholism are independent. Or you could say there is no association between gender and workaholism. And the alternative would be that they're dependent. Maybe workaholism is dependent on gender, or there is an association between the two variables. 34, we have X and Y. It looks already like we got L1 and L2 going on here, people. And already we can see this is probably some kind of correlation and some kind of linear regression situation. So I would write down linear regression, t-test, slope, this one, y-intercept, constant, 95% confidence interval for the slope. Put that down. Write down the sample size. For the degrees of freedom, you're going to do n minus 2 for this one. You're going to look up the slope. You're going to do the formula statistic v plus or minus t star times standard error of the slope. So you got negative 0.34655 for the slope. And then the sample size, that looks like they gave you, I don't know, so you actually have to count it. 1, 2, 3, 4, 5, 6, 7, 8, 11, 12, 13, 14, 15. Sample size 15. Sometimes it says it in the statistic output. It doesn't look like it does. Degrees of freedom equals n minus 2. 15 minus 2 equals 13. Then you would look up the t star for that. Negative 0.34655 is the slope, plus or minus look up the t star. And the standard error of the slope, you just look right next to it, and that's going to be this. It usually says standard error, not standard deviation, 0.05866. And you look up t star. Look up t star for 95% and 13. And then you can put the data in the calculator. You could actually put it in the calculator, or you can just copy it down and add and subtract by hand. If they ask you to test the hypothesis that there is a linear relationship or not, then you would put HO, beta, because the B estimates the beta, which is the parameter, equals 0. That means there's no relationship, no linear relationship between X and Y. And then the alternative would be whatever you want to prove. So if you think that there's a positive relationship, you would put beta is greater than 0. If you think there's a negative relationship, you would put less than 0. And if it just says there is a relationship, you just put not equal to 0. And then you could just put the data in the calculator, put this in L1 and L2. So L1 is going to be X, L2 is going to be Y. And then you're going to see that there is an option for you to go to stat, go over to test, and choose the the t-test, the Lin-Reg t-test, and you'll get the p-value. The p-value should be this one though, the one that is associated with the slope, which it looks like it's zero-ish. So I'm guessing that you're going to reject the null if p is approximately 0, and you'll rule in favor of the alternative and say that indeed there is a linear relationship between x and y. So that's about it. That's a crash course in inference. I might have missed a match pairs question in there for you guys, but that's pretty much it. You guys can see the difference between proportions, means, one sample, two sample, one mean, two means, one interval, two intervals, proportion, blah, blah, blah. You get the idea. Good luck. You can do it. You just have to kind of take your time and underline the key information and really write out in the margin like I am about what you have. You know, write down, is it a test or an interval? Is it means or proportions? Is it T or Z? Is it, you know, one sample or two sample? And that really does help, okay?